Hi, I'm Dr. Hay. I'm going to show you a momentum conservation problem. It's an elastic collision, which means that momentum is conserved and kinetic energy is conserved also. So it's an elastic collision that's a momentum conservation problem. Here's our before picture. We have a mass 1, which is 4 kilograms, moving at 6 meters per second this way, and it's going to collide elastically with a 2 kilogram mass initially moving at 3 meters per second. So we've got to figure out how to label all the information that we're given. Now, at a later time, after they've collided elastically, which means they bounce off of one another, we're being asked to find the final velocity for both of the masses. So you'll notice that we're being asked for two unknowns. If we have only one equation, we can't solve for two unknowns. We need two equations here. So let's go ahead and solve. And first, let's label our knowns and our unknowns. Okay, so we have mass 1, we have mass 2. Oops, this is mass 2. And we know that initially, let's say V1I, that's the initial velocity for the first mass. That one's equal to, let's call it positive 6 meters per second, because let's assume that this is our positive direction. It's also going to be our positive direction in the after situation. And if we get a velocity that is negative over here, then we know that it's actually going in the opposite direction. So we'll see what happens. We know that our initial velocity for block 2 is equal to 3 meters per second, also positive. Okay, so momentum is a vector. It is in one dimension, the sign is going to tell us the direction. So we don't need the vector signs. We're just going to need that this is positive and this is positive. Momentum conservation says that the initial momentum is equal to the final momentum. So our before momentum is equal to our after momentum. So let's go ahead and set up that equation. So our momentum before is a sum of the momentum of this block with the momentum of this block. Okay, so P is a vector that looks like mv. Let's go ahead and find the total momentum of the initial system. P initial is equal to m1 v1I plus m2 v2I. Our unknowns in the final situation are v1 final and v2 final. And they could be positive or negative. That'll tell us which direction they're going after this collision. Okay, so the final momentum of the system, P final, is equal to m1 and its velocity and m2 and its velocity. Momentum conservation tells us that these two things are equal. So we have one equation here already. This equals this. But you'll notice that we have two unknowns in that equation, this one and this one. So we need one more equation. Fortunately, we know that in an elastic collision, our kinetic energy is also conserved. So let's conserve kinetic energy here. Kinetic energy is not a vector. Here's my kinetic energy initial, because the two particles are moving. Here's my kinetic energy final, because the two particles might also be moving. Now I have basically this equals this because kinetic energy is also conserved, and this equals this because the momentum is conserved. Now I have two equations and two unknowns. Here's the unknowns there. Notice that they're squared in this one. So I'm going to ask you to pause the video, take some time to solve this system of two equations and two unknowns. And by two equations, I mean Pi equals P final and Ki equals K final. Solve these two equations for the two unknowns. These are your unknowns, and see if you get what I get. You should get that the final velocity of the first block is positive 4 meters per second, and of the second block is positive 7 meters per second. Interesting. So they underwent an elastic collision and they're still both moving that direction. So that's how you solve a momentum conservation problem that's an elastic collision. Because there were two unknowns, we needed two equations, and we used kinetic energy to get the second one.